So we said that stereoisomers differ by the arrangement of atoms in space. And the word we use to describe this is chiral. If a molecule is chiral, then it has a certain arrangement in space. And chiral basically means handedness. You can think of that as your hands, right? So with both your hands, they're both connected the same way. You have one palm connected to one arm, one thumb, and 4 fingers in both cases, right? With both your right hand and your left hand, you have 4 fingers, 1 thumb, 1 arm. But they differ in space. For instance, your left thumb is connected on this side, and your right thumb's connected on this side. They're not the same thing. In fact, they're mirror images of each other. So if you were to put your hand up to a mirror, you would see the other hand staring back at you. So the way to spot a chirality center in a molecule is to look at the atom. In order for an atom to be in order for a molecule to be chiral, you have to have one atom connected to 4 different things. Now, carbon is sp3 hybridized, which is a fancy way of saying that it likes to have 4 things bonded to it. And if that carbon has 4 different things bonded to it, then it has a certain handedness. It's what we call chiral. And let's just take a look at that. So in the last video, we used these two molecules to show that these are enantiomers, right? They're mirror images of each other. Okay, so I have the white one facing up, and in this one, the purple's facing out towards you. I'm holding the orange one here, and then we have this green one, and this is the mirror image of that, right? So they're different in their arrangement in space, but they're mirror images of each other, right? I could put them up like this to each other, and they line up, just like my hands do. The thumbs are both facing in the same direction, but they're not the same if I do it this way, because the back of my hand in the same direction as the back of this hand, they don't line up. So, like as we're looking at this one, they're mirror images, but you could see that if you put this molecule right next to the other one, they don't line up. This one has the green on the left side and the purple on the right side, whereas this one's opposite to that. So for it to be chiral, it has to have 4 different things connected to this central atom. Now let's take a look at that. Let's say we already saw that these two are mirror images of each other, that if you try to line them up one against the other, right, we have the orange on the bottom. If we try to line them up, then they don't match up, because on this one you have the green one pointing towards you, and this one, the purple one's pointing towards you. So what happens if we, let's say, swap out the greens with whites? Okay, so the only thing I've changed here is I've added 1 white in place of a green. Let's do it with the other one. Okay, the same molecules. I'm going to put this green one, or the orange one on the bottom, just like last time. The white one back here. And this one was the same way, right? And now you might be saying, well, yeah, the purple one is facing towards me on this one, but the white one's facing towards me on this one. Well, I could just simply rearrange this like, oh, where is it? Like this, and now we have the exact same molecule. The orange is on the bottom, the purple is facing away from you, and now these 2 ones are there. So this, by just having the same atoms, 2 of the same atoms on this chirality center, now it's no longer chiral. It doesn't have handedness anymore. Now it's, in fact, the exact same molecule. You may say, well, look, oh, that's a mirror image right there. Well, it's not really, because we could just rotate this way. Whoa, where is it? We could rotate it this way. If I can do it, actually. Could rotate it like this, and now it's the exact same molecule. It's just copies of the same molecule. So in order for something to be chiral, in order for a molecule to be chiral, it has to have at least one atom with 4 different things attached to it. Now, organic chemistry, it's very important in organic chemistry to be able to draw molecules showing their 3-dimensional shape. Because, let's take a look at this molecule. I have a black one, a red one, a white one, and a green one, and a blue one. Now, if I were to just draw that flat, right, I have a black one here, and then whatever, that's 2-dimensional. I can't see which way everything's pointing. So organic chemists use a certain convention to draw things depicting their 3-dimensional structure. So right now I'm not going to name any of these atoms. I'm not going to say this is chlorine and this is carbon. Right now I'm just going to color code it. Okay? So the central one is black. So I'm just going to draw a black circle. Now, I can arrange this any way I want. I could put the green one on top, the red one on top, or whatever. I'm going to choose to just put the white one on top, like that. Now, I'm going to line this molecule up so that the white one is in the same plane as the board here. Okay? It's not pointing out towards you. It's not pointing away from the board. The white one is going to be directly in line with the board. And I'm going to show that with one straight line. Like that. And there's the white atom. Just like that. Likewise, I have this green one also in the same line as the board. It's not facing out towards you or away from you. It's also in the same line. So I'm going to draw a straight line. And then a green circle for this green atom. And now when I have it held like this, I don't have any other choice. I have to draw this red one as facing towards you. Because you can see it is facing towards you if you hold the white one in that place and the green one in this place. So if I want that red one, if I want to show that that red one is pointing out towards you, I'm going to draw a wedge here. A solid wedge. I'm going to color it in. Like that. And when you see that, that means that that is coming out of the plane of the board here. Just like that. Just like this molecule here, this one is in line with the board. This one is in line with the board, but this one's sticking out towards you. Now this blue one is facing back there, back into the board. So the way I'm going to show that is with dashed lines like that. So when you see those dashed lines, that means it's going into the plane, or the paper, or the board, whatever you happen to be working with. And so there's the blue atom. So now if we look at this, we see that it's depicted the same way that it appears in space. You have the black one in the center. The green one is coming straight this way. The white one is going straight up. The red one's coming out towards you. And the blue one is going away from you. And that's how we would draw something depicting its 3-dimensional shape. And we'll be doing this a lot. And when we're working with real atoms and real molecules, then we're going to put the symbols. Right? So instead of this being black, it's usually going to be carbon, so I'll just draw a C. Okay? And then if that were, let's say, a hydrogen, I could put an H. And let's call that chlorine. I'd put a Cl. And we'll call that oxygen. So I would draw it like that, a wedge, with an O for oxygen. And then going back, the blue is usually nitrogen. So I'll put it N, like that. And that's how you'll see it in when we actually start writing these structures out.